Welcome to my presentation on complexity scalable learning-based image decoding. I am Tahsir Ahmed Munna, first year PhD student. Today, I'm really happy to be here in IEEE International Conference on Image Processing, and I'm really happy to share my work with you all. Let's begin with the overview of today's presentation. Today, I'm going to present and introduce my work with some motivation, related work. After that, I'm going to describe one important part of my work, which is low complexity image decoder. And one step after, I'm going to describe the main approaches in this work, which is called complexity scalable image decoding, in short, CSID. And finally, I'm going to evaluate my work with some final remarks. As you know, the image compression has progressed a lot in few past years with the help of the deep learning. As a result, we can see a magnificent RD performance improvement. On the other hand, we can see the deep learning-based image compression codec has the higher RD performance than the conventional image codec, which is JPEG 2000. But there is a problem still remaining. As you know, the deep learning-based image compression has the very simpler encoding than the very complex decoding part. That's mean this is very challenging to deploy this decoding technique in a resource-constrained device such as a smartphone. And also, the image is encoding once, but the decoding multiple times. So if key idea is if we can develop a decoder that we can play with the complexity, and then we can maybe deploy this kind of decoder in the real world devices. And this is the main idea of our work. We're going to create a novel complexity scalable efficient learning-based image decoding solutions where complexity can be controlled by employing more or fewer filters in the convolution layer. So as you know, lots of work has done in complexity of neural network. As example, we can say some pruning techniques, dynamic concatenate convolutions, adaptive binary channel masking. But in our study, no prior work has been done in terms of the complexity scalability, especially in the decoding part. So let's introduce an important factor of my work. As you know, the regularizer is very effective for reducing the complexity in the neural network. And in our case, we are using the L1 regularizer, where it's also called lasso, less absolute and a selection operator. Actually, this L1 regulator is offering the sparsity in the neural network and retaining the only important filter during the loss. So in our case, we use the loss L equal to R plus lambda D plus sigma summation of absolute value of the weights, where R and D is corresponding to the rate and distortion. And lambda refers to the model quality, like the alpha is a regularizer strength, where how much you can regularize the model. And W, which is the weight, and is corresponding to the magnitude of the coefficient. So let's describe a little bit our important part of our work, which is called low complexity image decoder, in short, LCID. Before starting, I want to say that the low complexity image decoder is a reference decoder. We are developing this decoder to have the fair comparison with our new approaches, which is called complexity scalable learning, where this low complexity image decoder can adjust their parameter during the training. And the important fact is we are not using the complexity scalability technique in this part. So we are going to compare our proposed method with this LCID, because this LCID has no scalability technique, but our has the scalability technique. So how our proposed technique can perform the. And for training, we initialize our LCID from the baseline, where baseline is a variational image compression with a scalable hyperprior. This is proposed by Johannes Balle, and why we are using this, because still this image compression technique is competitive than others, but maybe in future we are using the different state-of-the-art image compression technique. This LCID is also regularized with the L1 regularizer, and after that we are using the novel pruning technique that I'm going to describe after this slide. So also we are develop a new pruning technique, which is very simple and straightforward. We are developing this pruning technique because of having the lower complexity and model storage, and also we are trying to maintain the RT performance as high as possible. In the result section, you can see how our pruning technique can perform well. So we have a very simple and very straightforward technique. We have only three steps here, which is called computing the importance of the filters, then sorting and removing the unnecessary filters. Let's describe a little bit in detail. So as an input, it takes the regularized pre-trained model. After that is compute the importance of the filter. How it's compute the sum of the absolute value of the all like the words of the all filters in a single layer. After the second step is going to sort the sum of the words from the highest to the lowest, and that's mean the more important challenge come first. The final step, we are removing the less important filters based on our predefined pruning percentage, and after that we are as a output we get the pruned model. Let's describe our proposed decoder, which is called complexity scalable image decoder, in short CSID. Before starting, I want to describe a little bit of our decoder. It has a three important feature, which is called adaptive complexity. That means this decoder can adapt the complexity. Like we can give this more complexity to simpler complexity. And it has also the hierarchical learning. That means it will learn in a hierarchical way. That means the simpler model will come first, then the more harder model will learn from the simpler model. And it has also the encoder stability. That means during training, we always stubble or freeze the encoder and hyperencoder part to have the same BT stream. That just we can also only play with the model quality, not the. Let's describe the how we create our model, which is called complexity scalable decoder. So as a input, we take the pre-trained baseline model. After that, we're going to regularize this pre-trained model, and then comes our novel pruning technique. So here we are going to prune our model with some percentage, predefined percentage. In our case, we prune 60%, 50%, 40%, and then going to till the 10%. So once we the pruning have done for 60 to 10, then we are going to start the training process. So we started from the more simplest one, which is 60% prune model. We train this model from the scratch. As you saw the last the slide, that this training process is hierarchical learning. So we first training the more simplest one, which is 60% prune model. After that, once we get the trained prune model, then we are going to enhance the architecture, which means that we are giving some complexity by. So for understanding well, we can see an example here. For example, we have a 60% model, and layer 1 we have 80 output channel. So now we are going to train the 50% model. That means it has a more complexity than the 60%. Where we can see the L1, L1 means the layer 1 has the 86 output channel. So once we detect, we can see only 6 new channel we are going to add in the layer 1. So then we are going to partially training only this 6 channel. That's mean we take the whole part of this 60% prune model as initialized, or the 50% prune model. And then we are just training the new added channel, which is here in 6, and that we call is partial training, only new added channel. And then we get the trained model of, for example, the 50%. Then we are going this process till 40s, 30, 20, and 10. Let's start with the evaluation of our work. So this is our train and test condition that we are using in during our training. So let's dive into the RD performance of LCID, which is we call this reference decoder to compare our approaches. So as you can see, this model is very close to the baseline in terms of BD rate. As you can see, very simplest model, which is 60% of pruning, where we lose only 12%. And if you come to the 10%, which is very close to the baseline. So in average, we just lose 5.4% percent of the performance. So now we are coming to our proposed model, which is called CSID, Complexity Scalable Image Decoder. So this is we are a little bit far from the baseline, but not far from our reference, which is LCID. Where in very 60%, we are very close to the LCID, and also, but it's work very well in the higher pruning than the lower pruning, as you can see, like. In LCID, it works well in when it's only 10%, but it's work a little bit because it's work a little bit worse than the LCID, because this is the hierarchical process. So we just initialize from the simpler model to higher model. So and we are also use some constraint during the training. During training, the parameter cannot update in free way. So in terms of the all those things, that factor is happening here. We assume like this is the result is very impressive for our case, as we can play with the complexity. We can have give the complexity as we want. So for the difference of BD rate, we get the 4.24 then the LCID. So all overall, we are happy with these results. As you can see, the complexity, which is the impressive result that we are happy to show you, the decoding time. As you can see, the decoding time, the kmec per pixel, and the model decoder, we almost gain the 70% reduction of time and 85% reduction of kmec per pixel, and memory is a huge, like it's very simpler model that we are showed. And also we are describing the complexity in the layer wise. We can see we significantly less in the layer 1 and 2, and the layer 3. We are also, the baseline is high, but we are all still very less than the baseline. So as a final remark, we can see we are deploying a very novel approaches, which is called complexity scalable learning based image decoder, where we use the L1 loss and also a novel pruning technique. And this technique, we believe, we can deploy in the research energy constrained devices, for example, the smartphone. And also we can see, based on the result, we can see our novel pruning technique also works very well. And when we come to the complexity reduction, we found a massive reduction of our complexity. We gain a lot in terms of the complexity in the decoding time, the model. So all overall, our proposed method works very well in terms of the complexity, in terms of the RD rate. So here is the reference that we are using during our work. And thank you very much for listening me. And if you have any question, we will see in the conference in person. Thank you very much for attention.